Hello everyone, welcome to the course on discrete mathematical structures. Myself, Venkatesh Prasad BS, working as an assistant professor in the Department of Computer Science and Engineering, Government Engineering College, KRPET. In this today's session, we are going to discuss Module 2, particularly properties of integers. The topic is mathematical induction. First, let us see the definition of the mathematical induction. Whenever you want to solve any problem based on the mathematical induction, it is basically based on the principle called as the induction principle. This induction principle based on one more principle that is called as the well-ordering principle. In all these further sessions, we are going to assume z plus as the set of all positive integers. As I already mentioned, your induction principle is based on the well-ordering principle. The well-ordering principle states that a very non-empty subset of Z plus contains the smallest element, that is the least element. Or the set of all positive integers is always well-ordered. Suppose your Z plus contains the elements from 1 to 6, 1, 2, 3, 4, 5, 6. Consider one set A. A is equal to 1, 2, 3. Definitely 1, 2, 3 is a subset of Z plus. In that subset, there is one smallest element. Always we can have the smallest element, this one. You take any positive integer, set of all positive integer. You take the subset of that positive integer. Always it contains the least element. Or in other words, always the subset of Z plus, all the positive integers are well ordered. It means 1, 2, 3. They are in the some sequential order. Once we understood the definition of the well-ordered principle, next we move on to the induction principle. In this session, we are going to solve various problems based on the mathematical induction. It has basically two steps. First, let us assume S of n as the open statement that takes the universe as set of all positive integers in. Whenever we want to solve any problem based on the mathematical induction, we need to follow two steps. The first step is we are going to assume the statement, open statement is true for n is equal to 1. Then we assume your statement, we prove that definitely it is true for n is equal to k plus 1 also. First we assume that it is true for n is equal to k, n is equal to 1. Then we assume that it is true for n is equal to k. Then later on we prove that it is true for n is equal to k plus 1. Definitely your open statement is true for all the value of n belongs to set of all positive integers. See, that's what the method of mathematical induction is basically has two steps. The first step is called as the basic step. In the basic step, we are going to verify that the open statement S of n is true for n is equal to 1. In the induction step, we assume that whatever the problem it is given, it is true for n is equal to k. Then later on, we derive that it is definitely true for S of k plus 1. If it is true for n is equal to 1, n is equal to k, and n is equal to k plus 1, definitely your statement is true for all the positive integers greater than or equal to 1. Sometimes what happens? Always your open statement or any problem that is given need not be true for n greater than or equal to 1. Sometimes it is true for any value other than greater than or equal to 1 also. It is not necessary for always n is equal to 1. Sometimes your problem may be stated based on n other than the value n is equal to 1. If suppose your problem starts from n greater than or equal to 6, then we need to assume the basic step as n hat is equal to 6. Then in the next induction step, we are going to assume n is equal to n naught is equal to k, but that k should be greater than or equal to n naught. Suppose if you assume n naught is equal to 6, then the next value of k is 6 plus 1, 1 more than 6. Suppose that is k is equal to what? 7. Let us see some problems based on the mathematical induction. The problem states like this: prove by mathematical inductions that 1 square plus 2 square plus 5 square and so on and so forth up to 2n minus 1 whole square is equal to 1 by 3 into n into 2n minus 1 into 2n plus 1 for all the positive integers greater than or equal to 1. Whenever you want to solve any problem based on the mathematical induction, first let us assume the given statement as the open statement. S of n as 1 square plus 2 square plus 5 square and so on and so forth up to 2n minus 1 whole square is equal to 1 by 3 into n into 2n minus 1 into 2n plus 1. As I already mentioned, the mathematical induction problems will be based on two steps. One is the basic step. In the basic step, we are going to assume your statement is true for n is equal to 1. Consider the last term, substitute n is equal to 1 here. 2 into 1 minus 1 is 1 only. 1 square is equal to 1 by 3 into 1. 2 into 1 minus 1 is 1. And 2 into 1 plus 1 is 3. 1 square, 3 gets cancelled. Definitely 1 square is equal to LHS is equal to RHS. Definitely this statement is true for n is equal to 1. The next step is the induction step. In the induction step, we are going to assume the statement is true for n is equal to k, where k is greater than or equal to 1. That is set of all positive integers. That means in this original equation, wherever n is there, replace it by k. Now, see, whenever we want, basically we are going to assume that your statement S of n is true for n is equal to k. Then later on we are going to prove that the statement is true for n is equal to k plus 1. We assume that it is true for n is equal to k. Then we prove that the given statement is true for n is equal to k plus 1. See, in order to derive that, we need to add some value here. How to add the value? Take the last term in the LHS. Wherever k is there, replace it by k plus 1. 2 into k plus 1 minus 1 is 2k plus 2 minus 1, that is 2k plus 1 whole square. Now it becomes 2k plus 1 whole square. That means take the last term, replace by k into k plus 1, then you are going to get 2k plus 1 whole square. Then we add this 2k plus 1 whole square on both the LHS and the RHS of this equation. Then you are going to get the following equation. See, for the previous equation, I added 2k plus 1 whole square on the both LHS and the RHS. Okay. Now, this is 1 by 3 k into 2k minus 1 and 2k plus 1 plus 2k plus 1 whole square. 1 by 3 is the constant retained as it is. If you observe these two terms, we can consider 2k plus 1 as the common factor here. Then I left out with k into 2k minus 1 plus 3 into 2k plus 1, because 2k plus 1 and 2k plus 1 is 2k plus 1 whole square. If I simplify this, 2k square minus k plus 3 into 2k is 6k plus 3. Once again, simplify this, 2k square minus k plus 6k plus 3 is 2k square plus 5k plus 3. The remaining term will be as it is. Then upon simplification, 1 by 3 into 2k plus 1, 2 into k plus 1 into 2k plus 1, 3. Definitely this is the statement for S of k plus 1. It means we assume that your statement is true for n is equal to k. Finally, we are in a position to show that it is true for n is equal to k plus 1 also. Thus, we say that S of k plus 1 is true whenever S of k is true for all the value k greater than or equal to 1. Basically, in the basic step, we assume that the statement is true for n is equal to k. Then in the induction step, we are going to assume that your statement is true for n is equal to k. After assuming, then we prove that your statement is also true for n is equal to k plus 1. If it is true for n is equal to k plus 1, then by the principle of mathematical induction, S of n is true for all the value n greater than or equal to 1. Consider another problem. Prove by mathematical induction for every positive integer n, 5 divides n to the power of 5 minus n. See, consider the open statement S of n, which states that 5 divides n to the power of 5 minus 5. As I already mentioned, we are the basic step and the induction step. In the basic step, we prove that the statement is true for n is equal to 1. Wherever n is there, replace it by 1. That is 5 divides 1 to the power of 5 minus 1. 1 to the power of 5 minus 1 is 0. Definitely 5 divides 0, because if we divide 5 by 0, the quotient is 0. Any number will divide 0 except 0, which is true. Definitely 5 divides 0, which is true. If it is true, then we move on to the induction step. In the induction step, we assume that S of n is true for n is equal to k, where k is some set of all positive integers. For k greater than or equal to 1, for k greater than or equal to 1, we can say that this here in the problem itself is given for every positive integer. Positive integer means k should be greater than or equal to 1. I can write 5 divides k to the power of wherever n is there, replace it by k to the power of 5 minus 5. Or in other words, another way of saying this one is k to the power of 5 minus 5 is a multiple of 5. Or another way of representing the same above statement is k to the power of 5 is equal to 5 times m. That means it is a multiple of 5 where m is some positive integer. Suppose you substitute m is equal to 1, 5, m is equal to 2, 5 into 2, 10. Always on the RHS, we are going to get the multiple of 5. 5 divides k to the power of 5 minus 5. Another way of saying the same statement is k to the power of 5 minus 5 is a multiple of 5. Both are in the same. Now in the induction step, we need to prove that the statement is true for n is equal to k plus 1 also. That's why what we are doing, we are going to consider the previous equation, then replace wherever k is there, replace it by k plus 1. So here k, in the previous problem we have k plus 1 over to the power of 5 minus k plus 1 is equal to k plus 1 whole square into k plus 1 whole square into k plus 1 minus k plus 1. That means what we are trying to do here is, see, we know that k to the power of 5 minus 5 is a multiple of 5. That's why what we are trying to do here is, we are taking the LHS, then k plus 1 over to the power of 5 can be expanded as k plus 1 whole square into k plus 1 whole square into k plus 1. This 2 plus 1 is k plus 1 over to the power of 5. Upon simplification, we are going to get k to the power of 5 plus 5k to the power of 4 plus 10k to the power of 3 plus 10k square plus 5k plus 1 minus k plus 1. If I take k to the power of 5 minus 5 as the common factor here, k to the power of 5 minus 5 as the, sorry, it has to be k here, k to the power of 5 minus k. I am going to bring all the terms, some terms to one side, k to the power of 5 minus k, plus take 5 as the common factor, k to the power of 4 plus 2k cube plus 2k square plus k. Now all of you know that k to the power of 5 minus k, it is actually k, is the multiple of 5. That's why we can say that That's why we can say that k to the power of 5 minus 5 can be replaced by 5 times the value of m. If I take the 5 as the common factor, k to the power of 4 plus 2k cube, k to the power of 4 plus 5 into 2k cube plus 2k square plus k plus 5 plus 1 minus k plus 1, then plus 1 minus 1 gets cancelled, then the remaining term is k to the power of 5 minus k. Strictly speaking, it has to be k to the power of 5 minus k, it is, because it is n to the power of 5 minus n. Okay, by mistake it is printed as n to the power of 5 minus 5. Okay, now k to the power of 5 minus k is 5 times n. If I take the 5 as the common factor, take 5 as the common factor here. M plus k to the power of 4 plus 2k cube plus 2k square plus 4. Definitely, if you consider the LHS, k plus 1 minus k plus 1 is a multiple of 5. That is, if it is a multiple of 5, another way of saying this one is 5 divides k plus 1 over the power of 5 minus k plus 1, which is exactly the statement S of k plus 1. S of n is 5 divides into the power of 5 minus n, it is. S of k is 5 divides into the power of k to the power of 5 minus k. S of k plus 1 is 5 divides k plus 1 over to the power of 5 minus k plus 1. Definitely, which is exactly the statement S of k plus 1. Thus, we are in a position to prove that S of k plus 1 is true whenever S of k is true for all the value k greater than or equal to 1. Hence, by mathematical induction, we can say that S of n is true for all the positive integers. Next, we move on to one more inequality problem. Prove that 4n is less than n square minus 7 for all positive integers n greater than or equal to 6. As I already mentioned, always the value of n need not be always it starts from 1. It may start from any arbitrary value, positive integers. Once again, consider the basic. Consider that S of n is an open statement. This is an inequality problem where S of n is 4n less than n square minus 1. Here, our objective is to prove that S of n is true for all positive integers n greater than or equal to n naught, where n naught is equal to what? 6 here. Your basic step always starts from n is equal to 6 here. S of 6 is 4 into 6 less than 6 square minus 7. Then after simplification, 4 into 6 is 24, 24 is less than 29, which is always true. Therefore, S of n is true for n is equal to n naught, which is equal to 6. Once we got the basic step, then we move on to the induction step. In the induction step, always we assume that S of n is true for n is equal to k, then we finally come to the conclusion that it is true for n is equal to k plus 1, where k is greater than or equal to 6. That is, 4k is less than k square minus 7 for k greater than or equal to 6. Now our objective is to prove that it is true for n is equal to k plus 1. Our objective is to prove that it is true for n is equal to k plus 1 also. How to prove that it is true for n is equal to k plus 1? See, consider the LHS. Wherever k is there, replace it by k plus 1. That is 4k plus 1 is equal to 4k plus 1 less than k square minus 7 plus 4 plus 4. That means what we are trying to do here is we are going to add 4 on both the LHS and the RHS. Why we need to add 4 on both the LHS and RHS? Because I need to get 4 of k plus 1. If I want to get 4 of k plus 1, that's why I'm going to add the left hand side of the inequality as well as the right hand side of the inequality. We are adding what? Plus 4 on both the side of the equation. Okay. Another way of saying 4k plus 4 is 4k plus 1 less than k square minus 7 plus 4. See, all of you know that when k is greater than or equal to 6, multiply by 2, 2k is greater than or equal to 12. Add 1 on both the side, definitely 2k plus 1 greater than or equal to 13. If 2k plus 1 is greater than or equal to 13, obviously it has to be greater than what? 4. Another way of saying the same is 4 is less than 2k plus 1. 4 is less than 2k plus 1. That means 4k plus 4, 4k is less than k square minus 7 plus 4 is less than 2k plus 1. That is another way of writing this 4. I'm going to replace by this inequality, that is 2k plus 1, because 4 is less than 2k plus 1, because 2k plus 1 is greater than 4, means another way of saying this one is 4 is less than 2k plus 1. That's why replace here 4k plus 4, 4k is less than k square minus 7 plus 4 is less than 2k plus 1. Now upon simplification, k square plus 2k plus 1, k square plus 2k plus 1 minus 7. It is of the form a plus b whole square, 4k plus 1 less than k plus 1 whole square minus 7. This is exactly the statement that is required for us, that is s of k plus 1. S of k states that 4k is less than k square minus 1 for k greater than or equal to 6. Similarly, S of k plus 1 is 4 of k plus 1 less than k plus 1 whole square minus 7. This is what the statement it is required for us. That means S of k plus 1 is true whenever S of k is true, where always the k in this problem is greater than or equal to 6. That's by mathematical induction, we can prove that S of n is true for all the value above the value n greater than or equal to n naught, that n naught is equal to 6 here. This completes the session 1 of your module 2.